Hello everyone. Today I'm going to talk about our work on design methodology for scalable 2.5D and 3D heterogeneous tile chiplet systems. My name is Srivatsa and I'm from Heterogeneous Platforms Labs Interlabs. I graduated from Penn State couple of years ago, and this work which I'm going to present today was done as part of methodology development work within HPL of Interlabs. At first, I'm going to explain the need for chiplet-based system development while explaining what are tile chiplets and why are they really important. Mainly, this presentation focuses on passive base in silicon or PBS methodology considerations, along with power connectivity and scaling of active chiplets on a PBS interposer. I'll also talk about modular design and methodology incorporation using a simple example. As we all know, that the present day applications demand huge compute power and a large bandwidth to process all the data within a strict performance budget. We also see a global semiconductor demand growing over 25% year to year. Um, at the same time, as you can see from the figure over here, cost per mm² of yielded silicon doubled from 16 nanometer to 7 nanometer and going forward. Therefore, heterogeneous integration through die disaggregation is a promising solution where multiple smaller dies are also chiplets work seamlessly together when assembled in a bigger package. Smaller chiplets increases the whole silicon yield, thus decreasing the overall cost and time to market, while improving the system efficiency by letting logic, I/O, RF element, whatever's within the package, coexist in their optimal process nodes. With a rapidly evolving heterogeneous integration design space, there is a clear need to rethink the problem grounds up for efficient design and rapid prototyping. Therefore, we have already started seeing many solutions across the industry. However, between 2.5D with interposer and active chiplets on top, or 3D with active interposers and active chiplets on top, or a combination based approach, is a trade-off between desired performance and the overall assembly cost. For example, Intel adapted the 2.5D EMIB approach with Stratix 10, a 3D Foveros technology with Lakefield, and even a combination of 2.5D and 3D stack chiplets with Xeon graphics family. From these examples, we can clearly notice that active chiplets are integrated over a silicon interposer, which can be either active or passive. When we say active base, it usually comprises of memory as the base die component. Passive interposer or the passive base die can be further categorized based on how an active chiplet is being integrated on top of it. If number of active chiplets have uniform die dimensions, then we consider it as a homogeneous passive based die slot system. Or other systems can also be classified as heterogeneous die slots. From the top left corner figure shown, the double bond process of the PBS interposer has wider pitch C4s towards the package side and high density of micro bumps on the chiplet sides. Therefore, this low cost reticle sized interposer is suitable for hosting numerous tiles of chiplets. So in these examples, we either call it as tile slots or die slots interchangeably. So this sandwich silicon is the key design component in a 2.5D 3D system. Hence, this work is kind of dedicated towards the design methodology of this passive based silicons. Next set of slides focus on the PBS or passive base in silicons methodology and design considerations, along with several other factors. Let's consider an example multi-die design illustrated in the figure here, which has two active dies, die 1 and die 2, integrated over a PBS interposer in a face-to-face stacking approach. In turn, the PBS interposer itself is integrated on top of a package system. Therefore, from the methodology point of view, we split the design into two phases. The phase one being designing the active dies, following some of the methodology rules we set from the PBS perspective, and the second phase being looking at the PBS and the tile slot, which I'll explain in the next slides, building the package and the package routing itself. Therefore, designing or the methodology of the PBS itself is really important, where we propose to build something called as tile slots, wherein an active chiplet can reside. For example, this tile slots needs to be modular and homogeneous, so as to incorporate any of the active dies in terms of functionality if the active die of the chiplet follows certain criteria, including the dimensions and other things. Therefore, tile slot helps in modularizing the design with repeatability and ease of design. At the same time, we need to be aware of what kind of inter-die routings are possible between the die 1 and die 2 communication purposes. Therefore, we need to plan micro bumps, and we also need to be aware of some of the I/O hookups directly going from then active die all the way to the packages, like power signals, clock, and so on. So we need to manage designing of all those things. Since the tile slots are designed on a passive base interposer, so we do not support any active components. We support only metal routings. That needs to be decided based on the latency between the dies or number of metal layers required based on the number of IOs and so on, process considerations. However, that also needs to support micro bump connectivity on the one side and TSV all the way to C4 connectivity on a double bond process. The tile slots itself can be further divided into four components based on how an active chiplet communicates with the passive base. For example, in this case, we have north, south, east, and west directions micro bump slots, wherein these help in inter-die communications. Therefore, this will have micro bumps responsible for TX and RX receivers, power, and so on. The second region is for special IPs like PCIes, where multiple I/O hookups directly from the active die, wherever the PCIe is present, will communicate with the package directly. And the third region is a custom region where we can design PLLs, where we can design power management circuitries and so on. So this region 3 can exist anywhere within the tile slot, unlike the micro bumps for inter-die connectivity. Same with the PCIe and special IP slots of the tile slot itself. The center region shown here, which is called as core region, is for um, providing power connectivity, creating power grids, different power domains on an active chiplet, which will further communicate to the package through this tile slots presented on a PBS system. Another important component, which is shown in figure B below, shows an example of inter-die routing, which is on the PBS system, which connects between east microbumps and die 1 to the west microbumps and die 2. All these routings, for example, for the north dies as the neighbors, we will have the connections accordingly. So all these routings will be part of the tile slot and the PBS system itself. Since PBS supports only passive components and routing elements to communicate between the neighboring dies, careful simulation strategies needs to be employed in order to properly design for a required frequency or for a latency of communication between the two neighboring dies. For example, figure 1 shows here a simulation model which we built, wherein we incorporate the IO drivers, serializer, TX and RX from the two dies or the two chiplets, die 1 and die 2 in this case, and we insert the PBS channel or the routing model along with the micro bumps in this overall simulation model. The waveform here shows or illustrates the results from the simulation model, wherein an example input from the SerDes transmitter from chiplet 1 goes all the way through die 1's driver output through the micro bumps and enters the PBS. Through the PBS based on the inter-die gap or the inter-die distance, it again has to go through the receiver portion and the driver portion of the die 2 for a successful communication. Therefore, the width and the number of metal layers needs to be designed on a PBS. At the same time, driver need to incorporate all the parasitics from the PBS channel. This methodology is kind of agnostic to any particular technology. However, some of the critical things which we need to keep in mind are mentioned in the table on the right top corner. At the same time, depending upon the channel bandwidth and the required data rate, we need to finalize a number of transmitter microbumps and the receiver microbumps. And then we created an individual or unit pattern of transmitter microbumps, receiver microbumps, and we sprinkled VCC logic, VCC SRAM, multiple power rails grounds signals based on, of course, IR drop requirement and other considerations. And we kind of arrayed this unit template to form different regions of a tile slot. For example, this slot is from the east direction of one of the tile slots. And when we flip this tile slot, place another active die over it, the routing will be very straightforward, so that a corresponding transmitter talks to a corresponding receiver. Next step in the methodology is to determine the ratio of C4 to TSV and TSV to microbump in order to carry a robust power source all the way from package to the active dies. This also holds good for some of the IO connections as well. Therefore, within the tile slot, we create multiple custom templates of C4 TSVs and microbumps. This can be legoed within the tile slot in order to complete an actual power or signal connection. Right side bottom figure here shows a 3 TSV to 1 C4 combination in order to carry a high voltage signal from package to the active dies. So through simulations, we need to determine ratio of C4 TSV and microbump for signal, for power, and for IOs separately, and then place these custom templates in particular regions within the tile slot so that active dies can take advantage of these things. That being said, none of the two power C4s are connected or shorted within the PBS. Those connections will have to be completed at the active chiplet, so that to provide flexibility for the active chiplet designers in order to custom merge different templates to form multiple power domains required based on the logic designed within the active chiplets. While inter-die routings are mainly carried out through the micro bumps and the PBS channel routing. Some of the power signal connections and the IOs from active chiplet to the package needs careful package designing and package routing in order to be within the noise margin results through simulations. For example, in the figure, we can see a near chiplet and a far chiplet and their IOs being routed all the way from their PBS tile slot location to the package IOs. For example, compared to near chiplet routing, because of the distance and the proximity of far chiplet based on the package pins, the routing losses or the signal losses will vary. For a distance of around 20 millimeter long routings, we observe anywhere from 16% to 30% variation with respect to return loss and insertion loss as compared to a IO routing between the nearest chiplet to the package pins. So these things needs to be considered while coming up with package layout and package routing channels. We ensure that the tile slot is self-sufficient such that once placed all over the PBS interposer, we just need an inter-die channel routing on the interposer with multiple metal layers. However, all of the power connections, signal connections, everything will be completed through active die to package die routing. If we look at the top level of a PBS RTL or a design over here, we can notice that there are multiple tile instantiations based on the number of active chiplets to be integrated over a PBS. And the tile slot design itself contains microbump templates, TSV templates, different power templates. As we can see in this figure, power templates are spread all over the tile slots here. Based on the way we need to hook up the active chiplets and depending upon the number of micro bumps or inter-die connectivity, we have like dense C4 micro bump connections towards the left side of this picture, and custom IP region have sparse C4 based on limited IOs or again the power connectivity. So multiple templates, as I said, can be merged. This technology or this methodology works with different TSVs, pitches, C4 pitches, irrespective of the logic present within the active die itself. Therefore, methodology for the PBS design for tile chiplet system offers benefit in terms of ease of design, achieving higher bandwidth, and seamlessly integrating several chiplets with better reusability. So in this work, we mentioned the requirements of a passive base in silicon requiring multiple metal layers with wider spacing and higher width to obtain lower communication latency. We describe multiple methodology aspect with respect to PBS design to enable modularity and standardization. Therefore, we hope that these design methodologies help multiple PBS based heterogeneous integration works and believe that this work acts as a backbone of robust methodology enhancements in the future. We would like to thank everyone involved in this methodology works for tiled heterogeneous systems on a passive base silicon. We especially would like to thank members of Silicon and Systems Prototyping Lab for their continuous encouragement and support. Thank you.